different. I'm sure. Were you here in fellowship?
No, but every fellowship is fine.
Okay. Gotcha. Yeah. Well, he couldn't have this while I was here.
Yeah.
Did you do med school here? Med school and
Med school and residency,
yeah. I did med school in Arkansas, that's where I'm from.
Oh, nice.
And then moved for residency, which I really didn't like. And I was like, well, look, I can move anyway, because I know I would do the fellowship. So Florida for residency, came in for fellowship. Florida to Arkansas.
Arkansas.
Yeah, I'm going to be there in May. Yep.
Yeah. I'm sure they definitely move on.
Yeah.
Like most places.
Yeah. I do here in Seattle, Cincinnati, probably New York. Everywhere else, really.
Yeah. Yeah, it's kind of like our field. Like Boston.
Really?
What they have probably. It's so interesting.
Oh, wow. See, I would love to stay here, but there's just not a position. We have 6, so.
Yeah.
Well, can you have like
Yeah, we're going to do that.
I would go ahead and tell them there. So who's my chair?
So,
Because I just heard
beautiful list. And Dr. Love.
He had just got.
Oh, really?
That was like the one.
You know, like I said, I don't have to say, yeah. So I don't have to say anything about me, just speculating, you know.
But at least Dr.
They
Renee.
want to watch the break.
Dr. Frank.
We're going to just watch the break.
Maybe she has it.
What?
Super.
Yeah, I'm not sure. Maybe we can find out if they have registered.
I'm gonna tell him to do that, so funny.
Yeah, I think they would still do it. She's the only person at UNC. She made her own for ways. Just, I would just go ahead and, I feel like it would be good to go ahead
I love
for anyone.
Oh, I feel like, yeah. If you can do the number 1 contact, let them get all this anyway, she's got to be, to me.
Well, at least now we have
Really?
wow.
So, they gave me, she's hard to see, like an almost 2.
Right, yeah.
She does do it?
Yeah. I have done that for 2 years. Well, we moved around my house and I started a new job. Wanted to update. And she's like totally.
Yeah, but also too, because she has a test that she can get on my test. I'm all about that. You may have to like shift your driver. For the documentary, my back, like all those things to sleep. I can analyze her. Would I have that? My focus
Pictures all the time. And stuff. And I'm like, that's very sweet.
Yeah, I used to.
She had nothing. She knocked me off on this yesterday. And I was just like I could hear through the wall, and it just sounded very like, I don't know.
Yeah, exactly.
Yeah. Like I didn't know.
Yeah.
No. I wonder how many full time things we're getting. Yeah.
How was that?
It was good. Yeah, it was good.
Like they need to be up to what the interesting. I didn't read them.
Sometimes people talk about the word and the hypothesis and analogy.
Well, she's like,
yeah, she's type one errors or.
yeah, that's her.
It's not there.
Did she ever email you that?
Oh, yeah. Good analogy. Makes so much sense.
So now,
Yeah, right.
so she's in a bad mood.
It's all good.
No, because like, but and then yesterday, we were talking to her.
Remember now, so we're gonna take it. So nice to like walk this morning, not That's been terrible. I know.
Well, it's not
Yeah. Probably pretty good.
Not one.
Probably pretty
I
good.
was, you know, like when you're in the
When I was in Boston,
and then she
I'm out there.
because
And what was it?
and she was like,
Yeah, the first one. We're going to go through both. First half will be the first one, and then
Last year, really were.
we're going to break the line, switch slides, and go from there. Alright?
Yeah, she bought her a screen also.
Alright, let's pick up where we left off last week. Anybody online? Okay, so hopefully they can hear. Pick up from what we did last week. Actually, I'm switching into another slide deck and going from there. To me, there were two things. Last week we were talking about just the general overview of statistics and the concepts. Because again, I think often we give superficial understanding to the concepts and we get ourselves confused. We can back up, have a deeper understanding, then we stay off of the issues that come up often in the explanation. So I'll take a volunteer. Who wants to tell me what a type 1 error is? Wait, finish yours first. Finish yours first. It's okay. Anyone? I like interaction.
Can I use the jail?
That's exactly where I wanted you to go. I want you to go back to the concept of all hypothesis testing, all of the scientific method can in some ways be brought back to trial methodology. So
Type 1 is sending an innocent person to prison.
Right.
Because you see something that is not
there. Yeah, because you have concluded based on some evidence that something has happened, but nevertheless you're making the incorrect decision. Okay, so that's perfect. So a type 1 error in the jury situation is we assume the null to be true. The null here is a person is innocent. You make the incorrect decision, and you actually make the grievous type 1, the thing you want to limit the probability of, and you send an innocent person into prison. All right. So under that condition, then help me understand what a null hypothesis is to a statistician. Same analogous, same thing, but if we were doing research and I said, state to me a null hypothesis, what is, bottom line, what is it? And you don't have to put in any of the Greek. It is the one that we do what? We will work the whole experiment doing what? When we do a jury trial, the person is assumed what? Innocent. The null hypothesis is the one we set up so that we can test all of the data. This is the reference to which we make we're going to compare the evidence to. What's a p-value? This is the whole thing. The whole thing last week was to figure out what the heck is really a p-value. And what is it not? I saw you did a wonderful job last week.
But given the null hypothesis is true, the probability of seeing this data.
Exactly. Given that we are working under a set of beliefs, given that the null hypothesis is true, given that you really have not had an impact in your experiment, what's the probability of having observed this data, or data even more extreme? It is not the probability of truth, okay? It's not that. It is the probability of evidence. It's the probability of data. It is the probability of data under a specific belief, a specific restriction. I will hammer that home today because, believe it or not, and I've said this, and people don't believe me, I promise you this is the truth. I walk on this, I try to go get a cup of coffee at Lucy's. Someone will stop and ask me to do a power calculation. I am not joking. I'm not making any, and I'm serious. People, all right, because everybody is worried about, do I have enough power? Before we even get there, the first thing is to recognize that's never the first question. Don't stop me on the street and say, what sample size do I need? What power? The first question is, what's the specific aim? And then we have to move forward. But it's imperative that we understand how, can you calculate power? I was here last Wednesday night. I had two lectures on Wednesday in this building. And somebody had emailed me the night before and said, hey, I did the power calculation. Can you verify? It's a wise thing to do. I mean, you should. There's plenty of calculators out there. However, how a statistician to verify it, and I had to say, no, your calculation's actually wrong. Okay, so it's not right. But the key here is to understand what power is and not to make it bigger than it needs to be. Okay? So we're going to go through, we're going to do, last week I gave you in 2 hours all of introductory Biostatistics 621, pretty much, boom, right through it without all the formulas. I'm about to give you all of a full semester of what you learn in a power class. Okay, we're going to do the first thing. I'm going to start with what we mostly do, two groups. What if we had to compare two groups? And it really doesn't matter to me, okay? Power is power is power. And once I get the aims, the principles are the same. That's one thing I want you to understand. If you understand a certain set of principles, you will be able to move from design to design all across all the designs seamlessly. It's all the same concept, regardless of your hypothesis, regardless of your design. Okay, and we pick design based on your hypotheses and your analysis based on your hypotheses, and the power has to be tailored. But the concept of power is the same across and is always trying to do the same thing. You'll understand when I get there. I'm going to talk about the two-group comparisons of proportion, because that happens a lot. You do a lot of chi-square tables that are 2 by 2. And then I'm going to emphasize to you why the most important part of the power section is not calculation. This is what people get confused, okay? The first word of every power calculation is assuming. Assuming. Which is me saying, I know I'm wrong. I know I'm making a guess. That's what a power calculation is. It is a scientific swag. What a swag is. Scientific, wild, I'll let you build in a guess. Okay? It's a swag. That's what this is. But it has to be informed. But it is not, you never need to say, is my power calculation correct? The answer is no, it is not correct, because we do not know the truth. The question is, can somebody repeat it? Can they confirm it? Okay? So, let's read the slides. What is power? What is it? We all talk about it. Hey, David, we need a statistical power calculation. What is it? What is it? Without reading your slides. What is power? Anybody know? Has anybody ever done a power calculation? Yes. There you go. After you finish your food.
The probability of finding its difference if one truly exists.
That's exactly right. Very good way to define it. Now notice what was said. What's the typo there? The probability of rejecting the null when the null is true. Power is the other piece. It is also where you reject, but you're rejecting correctly. So you want that to be high. But she said the key thing, given a difference exists. I've got to make an educated guess about how big of a difference you're going to make. And until we get to that definition, until we can have that discussion of what is clinically relevant to Vaughn, we can't do a power calculation. That's the other key part of today's lecture is when you go to meet or you're trying to get with a methodologist. The first key thing is be ready for a discussion of how big of a difference do you believe is clinically relevant. You can't ask me to make a clinically relevant choice. Okay, I don't know. You have to guide me. You have to give me that information, and then the exchange starts. Back and forth, okay? So power, now notice I put it in bold. It is simply a description. It's a description. I'm painting a picture, folks. I'm saying this is the landscape. Here is the forest of the experiment, of the possible outcomes which we are likely to declare. I should have put a question mark there, that the intervention experiment worked. Okay? Should not have a question mark, should have an exclamation point. Key words. It is a description. I'm describing a scenario that if we achieve this scenario, I'm telling you the probability that at the end of the experiment we will declare we have sufficient evidence to state at alpha 0.05 that the diet is effective. Or it can be written, but notice I said in key thing, it is a description. Possible, not guaranteed. This is the possible outcomes. Likely, which means we're talking about probabilities. We're going to work out a probability. And at the end of the day, we're talking about declaring or saying we have objectively novel and completely alternative. That's power. Trying to set up and describe the situations by which we believe if these things occur, we have a good mathematical chance of ending the experiment with the declaration of we have evidence. We have evidence. We have not proven, we have evidence. We have significant evidence. It can be written as a description of the sample size. There's something else. The other times I walk with Lucy's to get a cup of coffee, people don't stop and say, hey David, can you do a power calculation? They say, hey David, what sample size do I need to do this? Okay, same idea. It's just flipping it. Sometimes people come to me and say, I cannot afford more than 150 per arm. That's a constraint I have to live with, and I'll talk about under that constraint. What can we do? Other times people come to me and say, we're designing a grant, we're going to have plenty of money, you've got to tell me, this is the clinically relevant one, this is what I care about. Please tell me what sample size should we be targeting. All that is same coin, just different sides. Again, please, I always love to define things like what they are not. It is not the first thing to be worried about. At earliest, it is the third. At the earliest. Get your aims right. Get your aims right first. Then match your design to the aims. Okay? Hopefully, I did not have time to run on time yesterday. I need to find you the master table of designs to hypotheses, and that way, that's always a good thing to look at. Understand power calculation it's not a guarantee of success. It's nothing but like I said, a description. It does not say, just because you have 80% power, what does 80% power mean? Think about it. I declare that you have 80% power. Congratulations. What does it mean?
So 80% chance of finding a difference if the difference exists.
It's exactly right. All right, let's go further than that. When I say that today we have a 50% chance of rain, what does it mean? Sorry, but I'm asking.
Yeah.
There's no difference if you didn't say it.
what I'm trying to get to is this, you know, I still, for all my years of training in probability, I don't know what James Grant means. I really don't. Does he mean that 50% of all days that have these characteristics we've observed rain in the past? Is that what it means? Does he mean that 50% of the viewing area is going to get a drop of rain? I don't know. But for power, I do know. For power, if I tell you that there's an 80% chance, and I did this 5 times, 4 times, we would expect to end with, we found something. We found some evidence. I will not say we found that you did, I will say we have evidence that is supported. But 1 out of every 5 times, even though the difference exists, you would miss it. You would not have the opportunity to declare, I have found evidence. So you've got to keep that in mind. That you're literally saying, I'm going to take a 1 out of 5 chance that I'm going to miss a relevant effect. Yes, sir. Oh, great. We've got questions today.
So most of what we've been talking about is sort of clinical. You have a Gaussian distribution of blood pressure. Power calculation is pretty straightforward given that. If you're doing
I wouldn't say it's straightforward. Sometimes they keep me awake at night. Go ahead.
If you're setting up something totally different, like an in vitro experiment, what is the approach you take statistically? You don't have a quantitative number.
You don't have to have quantitative. You do not have to have quantitative. You do not have to have quantitative. That is a very key thing to keep in mind. It could be nominal. It could be, it could be, did we observe 50% of the cells die? Period. We can come up with what is called, nothing more than, binary outcomes. We can measure characteristics. So it does not have to be quantitative. It could be qualitative, and I can still do a power calculation. We're going to get into that in just a minute. That's a great question, though. So, and I will say this. Does every experiment need a power calculation? No. No. I do not believe that. Okay? And that's another reason to meet with methodologists. I'll keep us on the domain today of where I think we would need a power calculation, but I have had people come to me and say, okay, this is what I'm doing, please write me a power calculation. I'll say, no thanks, I don't see the need to. I mean, bottom line, they really didn't need a statistician for the Manhattan Project. You know what the Manhattan Project was? When the atom bomb went off, it went off. And you did not need a statistician to say, hey, I think you have an effect. Same thing with if you're going to make cells glow John Deere green under a microscope. If that's the outcome, you're not going to need it. Okay? But just because it's not quantitative and it's just qualitative, don't fall into that trap. There could still be the need for a power calculation. Right? Please understand this. It's not an exact measurement. It's a guess. It's an important guess, but okay. How to approach power calculation? You must define the specific aims. Okay. You cannot start anywhere else. Don't go anywhere else. If you're going to take an afternoon off and you're starting a project and you have one goal. That's it. Work on specific. Work on the hypotheses. Figure that out. Anchor there. That's the first and most important thing. I can tell you one other tidbit after years of starting on study sections, and going to DC for different study sections. I'll tell you the truth. You lose you when the grant on page 1. Nowhere else. If the reviewer gets off of page 1 and they don't understand the ends and they don't understand the importance, you won't. If they get off of page 1 and they believe it's an important question and they understand your aims, now you've got a chance. But you typically lose on page 1. So the aims are the most important. And then, getting to your point, think of how you will measure the outcomes. It's imperative that I understand, are you measuring something that is yes, no? There's plenty of things that I have to measure, yes, no. It occurred or it did not. Or is it a quantity? Am I measuring weights? Am I measuring changes in weights or changes in blood pressure? But you have to help me understand it. think of what observed changes or associations will convince you that your research hypothesis is true. Going back to our jury trial, right? Innocent, guilty. Null hypothesis is going to be you do not have an effect. The alternative is you have had an effect. Okay? Whatever you're trying to do, whatever aim, the question becomes, what does that effect look like? What, and it's more than that, what would be clinically relevant? You'll understand where I'm going in just a minute. How big of a difference matters? Immediately after considering these, now you're ready to come and say, let's sit down with a methodologist and talk about power and analysis plans and all of these things. Okay? At that point, it's time to go. Before then, does it help some? Now, I'll be very honest, there's plenty of times I'm in the room as people are formulating the aims. But is that down here, this is where we start getting into power and analysis. All right, so let's just talk about that. So I'm going to dive in deep, right immediately. Okay, here we go with the Greek. Two sample t-tests, right? Two sample tests. So typically, let's just do something simple. Let's do blood pressure. When we want to compare two blood pressure, that's about it. Just for an example. It won't line up here. Suppose that we're doing two blood pressures. Two groups, we're going to try to modify their blood pressures. We're going to go about it with one. Here. I'll go to my own experience. Okay? I'll go to my own experience. Classic studies that I had to do for media years ago. Two groups, urinary incontinence. So, don't laugh at me, but it was a study that I enjoyed doing because I really did not have to worry about reporting severe adverse events. We were just trying to stop urinary incontinence and lower the frequency of going to the bathroom per day. And you see all these drugs that are advertised on TV, right? What aren't they telling you? They're going to be, they'd say they're side effects, right? Side effects are really super dry mouth, okay? And we wanted to know, could we just do a behavioral intervention? Compare drug to behavioral intervention. Could we get, could we compare the two? With the belief, drug is better. Drug is better, you gotta put up with the side effects, but drug is clearly better than trying to do a behavioral intervention. But if you think about it from a statistician's point of view, I would assume I'm going to randomize people into two groups, right? And I'm going to work out what their, for the groups, what are their averages, right? So that's what this represents. Mu1 is equal to mu2 is indicating that if I could study the whole universe of people going to and putting a group of people on behavior, they would have one mean frequency per week. That's what we were measuring. And those on drug would have another mean frequency per week. Now, under the null hypothesis, I assume those two things are equal, right? I have to assume that there's no difference between the two groups. That's called the null hypothesis or the null hypothesis. And for teaching example, I'm going to say, let's just assume it's 30 and 30, because to do the power calculation, I've got to start imagining where those means line up. And since those two means line up on top of each other, that says there is no difference to me between those groups. Okay? There is no effect. That's what the null hypothesis has to state. There is no effect. Now, there are different ways to express it, but the general concept is always the same. But then I have to go to the alternative hypothesis and start imagining there. And I have to imagine scenarios that meet that definition. So this one says, okay, this is the research hypothesis, and we have had an effect. So how far apart can the means go? Well, technically, I could have done 30 and 29.999999. And it would have been true. This meets that equation. Is it clinically relevant? Probably not. Do you want to try to spot differences that small? Definitely not. Okay? But you won't find a difference that is relevant to you. Okay? This is just a teaching example, but you've got to start, because here's the take-home message. The first thing the statistician is going to say to you in the power calculation, when it's time to do the power calculation, I'll use this really bizarre phrase. What's a clinically relevant difference? Or I will say, based upon Jacob Cohen's textbook, what's the effect size? What I'm asking for you is to tell me the difference between those two numbers. The clinically relevant effect, if I do a power calculation here, is 2.5. Whatever 2.5 happens to be, that's the threshold I'm going for. So you've got to be able to help me articulate that. Okay? Now, understand that in the two sample situation, that's the easiest. When we get to go into 3 groups, 4 groups, it gets harder. Okay? But this is when I walk around, this is the way I honestly think about it, okay? When we do things as statisticians, I told you last week that we have bastardized all of statistical theory into one thing. We have. We created a spork, something that should have never been invented, but it is what the nature it is. It's the nature of our science right now. I told you that we do p-values, and we do, remember what I said, how do you interpret p-value less than alpha? What's the way you say that? Evidence beyond a reasonable doubt. But I also told you that there was another one where we did rejection regions. When I did my undergraduate degree, nobody talked to me about p-values one time. Not once. We drew the curves, and we drew 2 vertical lines down and said, I'm going to put half the type 1 error here, half the type 1 error in that tail, and then I'm going to calculate my test statistic and visually interpret, just visually interpret. If I'm inside the 2 here, I can't reject. But if I get extreme data, or extreme test statistics, if I'm down in this little area or this little tail, then I must reject. That's why these 2 sections at the tails, beyond the green verticals, were called rejection regions. I still teach the graduate students rejection regions because it makes power easy. Makes power super easy. So, because you see, this top graph is what's going on given the null is true. This is how I will conduct everything given the null is true. The green lines represent the rules of investigation. Now, the lower graph represents given a difference of 2.5 does exist. Where did the 2.5 come from, David? 2.5. Backing up one slide. Given that that difference exists, this is the given the alternative is true. Now, if this piece here represents type 1 error, I could shade, if I had a cool magic board, I could shade the regions. I would say that's where type 1 error is. Where's power? Power is all of the curve in the lower graph that is falling above a green line. So as you imagine with me, if I kept increasing this difference, this curve would start sliding slowly more and more over the green line. And as it slides more and more over the green line, there's more and more probability of rejection. You see, the whole point is to reject, be beyond the green line, given the alternative. And you see that that's what if I got color, I would shade this right here and say, there is your power. And the idea is, as we're going through scenarios, we're measuring how much of that curve is falling above a rejection. We're falling into a rejection. Key concept, so I'll pause here and ask you a question.
Can you quantify the X and Y axis?
Okay, so that's very good. Great question. Down here, these are test statistics. This is going to be like a Z-score or a T-score. This here is just likelihood. It's now be careful. I didn't say probability. I said likelihood. The difference is every curve has an equation, and this is just it's just the values popping out of that equation. Okay? So I would not want to say probability.
And so to say this in words, if the difference that exists is greater, then you have greater power?
Exactly! Always. Two things there are three ways I can manipulate power. And I'm going to get to those. The bigger the difference, the bigger the power. But you have to be careful. Don't go overboard. Because study sections will come back and say, there's no way you're going to be able to make a difference that. The other thing, I can increase power by increasing your sample size. Okay? Because remember, I can tighten. I can always make the curves tighter by increasing sample size. Okay? And then also, if we can somehow change the variance of the experiment, we can increase power. That's the hardest one. I don't like going there. Okay? So I'm gonna do a power calculation for you, okay? We'll just do a standard power calculation. So I've got to renew my license for my software. I don't like it. My license comes through. It's not a medical license, but software license. And this is no joke. It's the only reason you go talk to statisticians is we keep libraries of software, and one of those licenses. I'm just going to give up and just buy a perpetual license and give it $1,500 this year. Just give up. Say I want to play life. But it covers so many scenarios, and it's just a great tool to have. We have to assume how much variability there is, okay? And that's the other thing that a lot of times researchers get upset about is, dang it, I don't know how much variability there happens to be. It's okay. There's ways around this. We can make, I already told you, the first word of the calculation is assuming. So I can do multiple scenarios and lay it out. We're going to do the alpha at 0.05. What does that mean? What is alpha? Not the first letter of the Greek alphabet, but alpha is the probability of a type 1 error. So I'm saying we'll have a 5% chance that I'll conduct the whole experiment, and then if I am in fact wrong, there'll be a 5. If in fact the null hypothesis is true, I'll still take a 5% chance. It means I'll put 5% down in here in this little area. That's all it means. Finally, assume that the researcher believes that at most the budget can afford 30 per group. Notice I changed something. I've said, okay, they come to me, we're going to say this is the standard deviation, this is the alpha, and we're going to do 30 per group. So now I'm going to turn around and say, if you can only have 30 per group, this is what your effect size, this is the effect size you've got to get to. So if you want to go, there's a very nice power calculator on the internet. You don't have to pay $1,500 to get the license, I promise you. This is a good one. You enter the information. You say the difference between the two means is 2.5. Common sigma is equal to 5. Alpha, we want to say N1, N2, and the software will get it to you. And there it is. The power comes out with the number that says 0.4779. What does that mean? What does that mean?
You have a 47 and 48% chance of the difference
of conducting, given that sample size, and assuming that there's a true difference of 2.5, and assuming that the sigma, the standard deviation is 5, there's a 48% chance that you will be able to detect a difference of 2.5 and declare it statistically significant using an alpha plan. You got a 50-50 shot. It's not good. Not good. Too low. Okay? So, what I really wanted to, I try to tell you what the take-home messages are, and I'll give you a break in 13 minutes. The take-home message is, technically, I'm telling you that if we were using the bell shapes and using these grids, I would tell you that there's about 47 of the area under that curve right there that is between the red and the green. It's 0.4778. That's all it is. I'm telling you that amount of area that got above here, you got about 50% of the curve above the line. So I'm telling you, okay? It means that if you conducted 100 experiments 48 times, you would be able to say, oh, kind of. If you expect to be 2 times, you would not. All right, we got there. And this is the thing. This is why I say, every one of you can go there, and trust me, you have the skills to go to that webpage, get that information, and get that number. What you may not have the skill to do is get the information down in a paragraph to convince a journal editor or a study section. And that's why I put this here. Notice, this is what I would literally put into a grant. Assuming a two-tailed hypothesis using a type 1 error rate. It reads like a statistician wrote it, trust me. 0.05 and a common standard deviation, then a total sample size of 60. So I just told you I'm going to get a complete 60, but I'll put 30 per group, provides 47.79% power to detect the difference between 2 groups means of 30 and 27.5. I have given them everything I assumed. Nothing is left of their imagination. They can go and replicate that. The point is we still got a lot of work to do. We cannot submit that power calculation. They're not going to fund an experiment that's got 50-50 chance. Typically, honestly, I used to when I was, when I was new to my job. Most textbooks put it at 80% power. I've given up. I actually moved it to 85. I moved it to 90. You know why? Because 80 means you better get everybody you promised. You have no room for error. So I buffer it a little bit and take the power higher with the anticipation that something could go wrong. Okay, moving the means increases the power. Look what I did here, assuming a two-tailed hypothesis. Same thing, but this time, notice I pulled them further out. I pulled them out and I said, where did 26.3222 come from? It came from the software. I turned the software around and said, you find me the difference and gives me 80% power. It's just a set of equations. You just engineer them to answer the questions differently. So this I could come and tell you as an investigator, if you're going to use this sample size and under these assumptions, then you need to be hoping you have a clinically relevant effect of a minimum of 3.68, whatever units. Okay? Yes? Question? The other thing I could do, watch this, notice I kept this as 30 per group. I can also achieve 80% power by doing something else. I said, the investigator came back and said, no, David, I lied to you. I can actually afford many more. Okay, great. You want to stay with the 2.5? Yes, I'll stay with the 2.5. Now I still get 80% power, but now I've used the other arm or the other lever I have to control power. And I said, let's increase our sample size. Generally, I prefer this approach much more than anything else. If I have to live with a budgetary constraint, I understand that. But I would at least let's start the investigation without the budgetary constraint in place, have a full-blown discussion of science, and then if we have to create an experiment that meets the restraints, let's do that. But I think it's better for the sake of science that we start with, this is clinically relevant, what can we do? Go. Okay? What about if it's proportions? You understand, why in the world would the software be $1,500? Anybody, answer the question, seriously. How many statistical tests are out there? How many? Thousands. Every one of them calling for a different equation and approach for simulation to get these. So the reason you're getting the paying so much for it is for the breadth of it. Okay, well, I'm not buying the software because I need to do a two-sample t-test. I'm buying it because I need to do other things. But the idea is, as you change the outcome, we're going from continuous to dichotomous, the method change. As you change designs, power calculations change. As you change analytic approach, power calculations change. So you've got to have all those pieces together before you begin. But I'm going to illustrate to you quickly how you do a power calculation for proportions. Because honestly, a lot of times people come to me and say, okay, we do want to do proportions. Actually, it's a much easier thing to do because of some statistical theory. Because if you tell me, David, suppose we're going to compare two drugs, and we want to see, do the drugs have comparable success rates of relief, or different success rates in relieving migraines within 24 hours? As a guy who suffers from migraines every now and then, I'm making up an example. Okay, now you could say, I'm going to measure this time for migraines going. I'm giving you an example of being able to force it into dichotomy. Migraine gone within 24 hours, yes or no, period. Because it's a proportion, all you have to do is quote proportions to me. David, I want you to spot the difference between 35 and 25. Done, sit down and do it. That's all I need. You don't have to worry about the assumption about how much variability there is, all these other things, mainly because of statistical theory. Okay? That's the key last point. For proportions, if you give me the two proportions you stated there, I need you to compare 50 to 65. Okay, got it. Much easier problem. So, as my teaching example, suppose that we say the drugs are going to each have 20% response rates. And then we want to say, okay, we'll be happy if the other one increases up to 30%. That's what we call clinically relevant. We come in again and we say type 1 error 0.05. Notice I don't have to talk about variability or anything. It's all taken care of with that set right there. But keep in mind, you've got to talk about what is going on underneath the alternative. And here comes the shocker. I need you to give me 588 people. What? Yeah, you give me 588 people. So that's one of the things you got to talk why you get the statistician early. I told you it was easier to design. I didn't say it was easier to conduct. Very different things. People like to do dichotomy for the ease of the design, and they spit their coffee out when I show them the science. Okay? But take-home message of the first piece is please keep in mind, the key thing for power is you have to tell me what's going on under the alternative. What is clinically relevant. And once we have that, we can start this process. The other thing I always do, oh, David, I don't know what the standard deviation is, and I've looked through the literature and I found 4 different estimates. Well, good. You made my job easier. Because a lot of times we don't know, and we confess we don't know, and we don't pretend in front of study section that we know more than we do. We put the cards on the table. Remember, honesty always works. It does. And so what I'll do is I'll come in and I'll build a set here. This is very common in the grants I give, or I put in for the university. I say, assume, here's a range of assumptions. Suppose the variability is high. And suppose that maybe we could make it all the way out to 4.5 difference between means. And I come in and say, under those scenarios, I would have, under this situation, I got 96% power, 99% power, 100% power. Nobody's going to believe you got 100% power. But the catch here is this table illustrates some beautiful things to you. As effect size goes up, what happens to power for a fixed sample size? It goes up. And as variability goes up, as sigma goes up, what happens to power? It has to go down. The more variable it is, the harder it is to find a consistent signal. All right? Why it's not the most important thing. Then we're going to go into the more complex designs and reinforce the idea of what power really is. Especially with grants, the calculation has to be replicated. Okay? The other thing that always kills me, please, if you run into this, come talk to me, find me. People will come back and we're trying to publish a paper, and all the results are significant, and they say, well, what was your power? You want to know why I lost my hair? Questions that don't make sense. Why I lost my hair. I get a lot of questions that don't make sense. Power, it has nothing to do with anything after the experiment's over. Once it's done, it's done. You have either made the mistake or you have not. You have found the results or you have made a mistake. There is no probability. But nevertheless, if you get into that situation, you've got to come talk to me so we can move that paper through the process carefully.
Question.
Yes.
So what if you get to the end of your study and you don't find a difference?
If you do not find the difference, okay, at that time there needs to be a very good investigation. In fact, I will tell you a little secret that most people don't know, is that as the experiments are going on, I'm sitting back, I have the data, and I'm watching the data to see if my assumptions were close to correct or not. And if we get to the end of the study and we fail to see a difference, I always come back and talk to the investigator and say, we assumed that this difference was going to exist. We are nowhere near that magnitude, though the other assumptions are met. And it is an indication that we did not, more than likely we just did not have the effect that we thought we would. Sometimes I say, oh wait, look, we're getting the effect we thought was relevant, but it's a lot noisier than we thought. And under those conditions, I'll write what's called a conditional power calculation. Go to study section and say, this is what's going on. Will you fund another 100? And they will. But we've got to come in and look for the reasons why. Because the worst thing I always hate is when people say, okay, I got a p-value of 0.07. I failed. I wasted $4 million. You know, that's simple. So we have to come back in and look to see what. All right? If any data, please, you can do this. I'm going to encourage you to try. But whenever you are working and trying to flesh out a power calculation or getting ready to meet with a methodologist, one of the things is you need to read that paragraph and do that checklist. Can I find the typo error? Can I find the variability? Can I find the difference? If you can't find all those things, you need to ask the statistician, do you have all the details in here? So that an independent statistician can do this calculation. Okay? Yes?
In clinical trials, there's this adaptive methods
Uh-huh.
for the experiment.
Mm-hmm. Depends on what you mean by it.
Make up for this with some adaptive method.
So I just said a minute ago the concept of conditional power and or conditional power calculation. It depends on what you mean. The FDA is all over this right now, and the statisticians are all over it, because it all depends on what you mean by the word adaptive. I have no problem midstream saying, whoops, our variance estimate was terrible. Should we increase the sample size, or perhaps we're on the lucky side, maybe we can decrease our sample size. and stop the trial early. I have no problem with that. I have a major problem with looking at the data and saying our effect size, what the clinicians thought was important, isn't panning out. Let's now base that upon the data. No, that's not science. That's the data driving us. That is the tail wagging the dog. No thank you. Okay? Yes, that's a very strong opinion, but that's what I'm known for. So adaptive designs are out there. But adaptive does not mean, oh, I found myself in a hard spot. Let's go back and change everything. Adaptive designs are declared before you write the grant. You say, at this point, I will stop and consider adapting the design. But they're out there. And the last thing I would say is, if you do it, please have a methodologist inspect the power section. Okay? So we're going to pick up with the more complex ones of ANOVA and regression, because really, I mean, almost everything that people do falls either into the two-sample t-test, proportions, ANOVA, regression. I'll show you those, and you understand power under that. You got power all day long. 10 minutes. Okay.
So when you're doing something retrospective.
Oh, I love it.
know.
Well, that's fine with it.
So here's the problem I run into. It's like, it's chart reviews, and how many charts do you need to look through? How much of your resources, how many resonate, you're busy, I need you to look for 500 charts. So, we've reviewed close to 1,000 charts, and we look, and our p-value is 0.09. And so my question is, how do we need to look through more charts? And so I asked my statistician,
Who is?
Jeff,
Like,
and I say,
She can get it.
and I say, should we calculate the power? We didn't find a difference. Should we calculate a power analysis to see? No. And I'm trying to figure it out. Do I need to review more charts?
No. So here's what I would recommend you do. It's very careful how we phrase the question to the statistician, because we are quickly going.
Yes.
So the catch is, I would have said, and I thought, I'll be happy to sit down and do it with you, Angel, is to say, you tell me, regardless of the variance that we're observing in your analysis, let me look at the variance. And based upon that, you also tell me what is a clinically relevant effect. I will tell you the sample size.
Okay.
That we should have started. And then, you know what? You may be beyond it.
Right.
And if you're beyond it, you're wasting
We're
resources.
done. Exactly. Okay, so variance, super helpful.
Okay? Yeah.
So, let me get back to the individual question. So, a lot of times what we do is Western blots.
Western.
Yeah, no. So if I'm setting up an experiment, why have?
And now you're in one.
Okay, so you just take 5 and 5 and see what it looks like. You don't need it. All right.
Yeah, we might do
Pull everything together and say, uncared, this is what we saw for these subjects.
Okay. Nah.
And then a subset of those were paired, so how did those look?
Follow up with like questions. In fact, for social that I have to get things. I'll come in all the way. And so I increase in observation.
We do, and it would help us having this small sample size that you just ran. It gives us some idea of the variability.
And then.
But I think our situation is we're not just looking at one.
Because it's very easy.
We're analyzing 10 different
If
cells.
I associate
Can you give me the whole grid?
Oh.
Can you help me see the whole grid, and based on the whole grid, we could either do a exact method.
Well, it's a lot of people, one whole.
That's what, but
But I think that would help
still,
us.
Yeah.
we can do exact.
And I think our seeing.
Better yet, just send me the data. Just send me that data. I'm going to do the night.
So, I think that was. I used to write too.
Yeah, she always.
It's also that. Probably right. Like when she sent us the proof, it was when it said everything about that. Nothing. But when I went back to Scarberry about one night.
You have to tell me what I can put on there. Yeah, just tell me. Do you need to do anything? Okay, well, yeah, I do. Thank you. Yeah, I was just thinking every day I still talk about this hair salad. But yeah, that's stage 1 or 2. Stage 3 and 4. He doesn't, you see what I'm saying? He doesn't personally put your name. No, but I have a report. I was only very like, and she was like, no. Tonight, she's on the old side too. She told me that too, but I don't understand. She didn't do the qualifying. She didn't have the qualifying. What? They only have common. And that's what. What we do for the qualifying. She does for her comps altogether. And so she didn't do her comps until. It was pretty recent. Yeah, it was last semester. But and towards the end, it was really intense. So our schedule was supposed to be comps prior to our first year, so that was really exciting. And like I know, after you finish your college, you're supposed to know. I was told, like, here you're supposed to finish all your courses away from your class, so that when you finish the time, it's not very good. But she doesn't know.
Yeah.
She told me to be very general. The one question. The modules, objectives, individuals, yeah.
You only hold on that. That's strenuous and painful.
Which is very
Super nice. You should drive it back. Please come back. You know, little. Oh.
She thought that we were writing about like 25 years ago. It wasn't a real. I thought we were taking philosophy
And so there's
all
some
kinds of
I'm sure there's people that are still.
Oh, Kevin laughed at me.
Probably actually.
Right.
Everybody's getting.
She added.
Right, exactly.
Well, I don't know.
She added. There's this picture.
Yeah.
Yeah, or there's whoever. It looks like they need to be.
I told you.
And I look at it, I'm like, yeah, this person's supposed to be. But I'm not, I can't make her either. She must go through it. And this, I remember when the mother showed up.
Well,
now that's how we're doing it.
And then like now my connections.
There's no way away.
Yeah, as soon as I started doing that, they'll all start showing up again. I'm sure.
There's no way away.
No.
Yeah.
This one?
Yeah.
There's my boss. Where is it? You do it. Getting old. Questions? Good question. You keep looking at me, you look like a clock. I'm watching people while I'm lecturing, I'm like, okay, that's not a question.
I'm
Good.
My general resting thought phase.
Don't go there, because my wife is like, she said to me this morning, you've been quiet.
Well, I just noticed.
That's normal. Yes.
I have a question.
Great.
Okay, so just in going back to thinking about formulating our specific aims,
Mm-hmm.
okay, so, so I study obesity and how that affects immune responses.
Okay.
Okay, so my aims in a grant are never going to be that obesity has a difference on immune responses to tumors.
Okay.
It's always going to be, my hypothesis will be that obesity diminishes protective immune responses to tumors.
Mm-hmm.
So when I am formulating my aims, and we're going to look at this response in obese and lean, whatever. So, you know.
This is the thing you gotta let the statistician call time.
Okay.
You've already formulated your aims perfectly sound enough for us to start actually fleshing things out. My question to you, if we were in a consultation, are you going to use obesity? Are you going to break it into, the first question I would ask you is, are you going to do normal, obese, morbidly obese? Are you going to try to use obesity on a continuous BMI scale? Which of the two would you prefer to do, and which one do you think is more scientifically relevant?
So I would prefer to use obesity on a continuous.
I would recommend you doing that. You will be more powerful if you will do that.
Okay. But what I'm saying is I never have a hypothesis that just says it's
No, you've
not.
already stated your hypothesis. You already stated the statistics. You just don't Rick. I don't mean to argue with you.
No, that's okay.
I just come out that way.
No, I just
Because I'm trying to be
make sure
disagreeable, I was born with this trait.
Okay.
So the catch here is you've already defined the outcome for me, and we would need to sit down and talk about how much do you think obesity is explaining, and how much do you think it's diminishing the effect, the immune effect? As you said, diminish.
Yeah.
You have stated that BMI is continuous, and I'm assuming that you're going to measure some type of continuous immune response. Therefore, you are doing either a Pearson correlation or a Spearman correlation, and I can write power calculation for both.
Okay. All right.
Did you see what I just did? That is a consultation with regard to power. Now, what we would do is we'd have the aims, we'd have the computers, and we would sit down and we would start looking at different effect sizes with regard to, suppose that we're expecting a negative correlation of 0.1, that's going to mean something to a statistician, I know that. But maybe 1% of the variability can be explained by observing changes in BMI. What sample size do I need, David? David, I think that even after I adjust for all the other covariates that we know might affect immune response, I want to be able to have if BMI explains 5% of the variability above and beyond, I can do that calculation. I can write that calculation. And I can lead you through that. Yes, Megan?
I do.
See, Megan suffered a classroom. A full semester she suffered it.
Survive.
Yes. Well, you should have seen her before.
Some of my mentors talk about this a lot, because in pediatrics, pretty much everything they do is fairly rare, fairly small sample size, that you have more power when you're using continuous outcomes. Are there ever situations when that's not the case, or is that pretty much the case?
But again,
You still have to think about what's relevant.
you always have to talk about what is relevant, and there is a classic example. I should have, it's not my place to invite him, but years ago, did a lot of work with David Kimberlin over in pediatrics, wonderful gentleman, and we ran into that situation where he had, because of his long background, just chosen to dichotomize the outcome. And Matt Mayo was the statistician for the project, and I can remember discussing it with Matt, and Matt's going to David saying, we're hurting ourselves. Even though it's a small sample size, we should go back to, we can get by doing this on a continuous scale, and we should. And it helped us out tremendously. So it's always, the reason I'm in academia is because of the scientific discussions and because of the teaching. The whole idea is not to rush through the design discussion. Yes, there are deadlines. Just don't need to rush through it. We need to weigh, And also be careful when you say small sample sizes. To some people, a small sample size is only having 10,000 records. Only. Me, small sample size is, oh great, I got 15, what am I going to do with this? Be careful with that. Okay, we're going to do analysis of variance. understand something before I even go into this, and then again, yes, I did not put a tie, I don't mean her because, yes, I put a tie on, I did not put a tie on for you, I'll put a tie on for the next meeting. But I wasn't gonna have time to get the tie on, I didn't have time to put my tie on before I left home, and I was not gonna have time to put the tie on before I got to my next meeting, so. So, here's one of the things about statisticians. Here's the things you are taught. You think of analysis of variance as what? What is analysis of variance? What's that? I know you're bringing it from a part of
Just the English.
Huh?
Just the English. Analysis.
What is it?
What is variance?
Well, analysis of variance is a specific technique. Okay, remember the textbooks always teach you come in, do one sample hypothesis test, where you got the C, you got the T. We're just saying, we got one group, we want to know, we did a diet study, everybody came in, with everybody on one diet. At the end, we want to know, did things change in one sample test? One sample. Now we get more complex, we say we're going to have two groups, we're going to have two studies, we're going to have two treatments going on at the same time. And, we're going to compare chemo A to chemo B, or we're going to compare drug A to drug B, and we're going to have two groups. Now, analysis of variance is nothing more than, I got more than two groups. I got 3, I got 4, I got 5. I want to generalize that idea of two samples. How do we handle things with 2 samples? To how do we handle it when we got 3 arms? Because guess what? We demonstrated under a special technique, and I kind of lied to you, forgive me, please. When I did the studies in the VA, the study was actually designed to show behavior was as good as drug. In other words, if the behavior was going to have the same outcome, just as good of an outcome, with no side effects. Well, cha-ching, check the box we got there, it was significantly better accomplished. What comes next? The viewer says, well, what if you add drug and behavior together? Can you get better effects? Now I've got, so that's why I have to go into analysis of variance. Plenty of times, I don't have just 2 treatments. I sometimes have 3, or better than that. Sometimes I have you on 2 drugs, therefore I get 4 combinations. I could have 2 dose levels of drug 1, 2 dose levels of drug 2. I got 4 treatments going on simultaneously. How do you handle it? And then I want to talk about the multi-proportion. And now, again, before we go anywhere, what do I have to do a power calculation? You know everything you will ever need to know now about power. There are no other, what I taught you or showed you in the last slide deck is going to be the exact same thing I show you right now. The only thing is the pictures change. So what is power?
It's the probability that you will find a difference given your alpha, given this clinically relevant difference, and given the variance.
Exactly right. And you threw in the assumption, I think it's more important to just say, is the probability that you will declare a difference statistically significant if the difference exists. Okay? If a difference of this size or greater exists. Okay? Because it's all the concept of I've got to imagine what's going on in the null. I've got to imagine what's going on underneath the alternative. And under the alternative, I know that a certain region of a shape is going to fall and I want to see how much of that I can shove above a rejection line. That's all. So we're going to do the review of the chi-square, okay? Because chi-square, I would use the example you showed me just a minute ago, except for that 0 cell would throw me off. But it's a chi-square test of proportion. And what a chi-square does, and we'll get, and time will permit, we'll get into regression methods. Chi-square test for proportions, you gotta remember, I don't just have to have, I can have more than 2 groups when I do a test for proportions also. I can have 4 groups, I can have 5 groups. It's always, all of these things occur. You've seen this before. What I have done here is I've bundled the 2 lectures I did 8 years ago for the MCRC into 1 lecture here. So what I'm doing is I really want you to keep in mind that this is the way I want you to keep thinking of power. It is just a description. It's all it is. It's describing the landscape. It's what you expect. It's what you're hoping to happen. You got to monitor these assumptions. Again, it is a description. It is a possible experimental outcomes. This is why I don't like power calculations after the experiment, because there is no more possibilities. This is what we've got. It is likely to declare if it worked, and we always have to worry about meaningful effect. So, let me back up. I accidentally deleted an extra slide that I didn't mean to do. Let's start with ANOVA. When we want to compare the average value across 2 or more groups. Now, did I just contradict myself? No, I did not contradict myself, because I can always do a 2-sample test as an ANOVA. It's going to give me the same answer. That's one of the things they teach you in graduate school when you're going through all these different courses, is there are certain procedures that actually produce the same results, though they go by different names. They're just different versions of the exact same concept developed by different individuals. So the 2-sample t-test, if you're doing 2 groups, if you try to do an ANOVA with 2 groups, you get the same answer. That's a fact. But typically the null hypothesis would be the idea that mu1 is equal to mu2 is equal to mu3. In other words, that all 3 means line up. Now, when I teach a graduate course, I do not let the students write it that way. I make them write it as mu1 is equal to mu2, comma, mu1 is equal to mu3. I make them write it that way. Why would I make them write it that way? Because I'm teaching you a key concept. How many equations are going to be needed to make that whole statement true? 3 or 2? Only 2 are required. Huh? 2 equal signs, and if you ever want to understand what statisticians mean by degrees of freedom when they're talking about them, they're talking about the number of equations in them all. We're talking about the fact that it would take 2 equations to set up the null hypothesis completely. It doesn't take 3, because mu1 equal to mu2, then saying mu1 equal to mu3, by default, if those 2 statements are true, the last statement has to be true. mu2 must equal to mu3. Something wrong about that? Just winging, okay. Okay. And then here comes the complex piece, because I'm taking kind of the kid's gloves off. Now you got to remember, you got to now imagine under the alternative, right? If we go to power, we've got to come up with a scenario that's null hypothesis is false. And there are an infinite number of ways to make a null hypothesis. Well, there's one way for it to be true, and an infinite number of ways for it to be false. So we have to sit down as colleagues to work out how would we define a clinically relevant difference. If it's a test of means, why do statisticians call it analysis of variance? Key question. Never forget, analysis of variance is actually a test of means, but yet we named it analysis of variance, but we're mean. No, basic answer. If mu1 equal to mu3 equal to, if they're all true, the three numbers, there's no variance there. If they're all equal, they don't vary. We're asking to what degree do the means vary? Okay? Do these means vary, yes or no? So it's an analysis of the variance of those means. So if they're all lined up, there's no variance attributable to those things. If they're all on top of it, there's no change, there's no difference between the groups. The groups do not, quote, vary. Under the alternative, which is the hypothesis for which power is calculated, the three numbers contribute variance to that data. Okay? That's why we call it analysis of variance. Now you see, here I go again. First, remember there are two hypotheses, so mu1 equal to mu2 equal to mu3. I really don't, when I did that example before, I showed you, I could put here mu1 equal to 30, mu2 equal to 30, mu3 equal to 30. It really doesn't matter where I put those as long as they're all true, all equal. It's key that we understand that. Okay? Now let's talk about something. Is that the only scenario? Would I equally, and I'm going to slow it down for a little bit, and then I'll speed it back up because I may. Jane, am I on again next week, or do I have a week off and then I'm back?
You have 2 weeks off.
2 weeks off, wow. Okay, keep moving, I'll move us along quickly. Give me another scenario, just imagine with me. Give me another scenario that is equally true under the alternative hypothesis. Throw one out, quickly.
mu1 equals 27, mu2 equals 25, mu3 equals 30.
All right, great. Give me another one.
mu1 equals 30, mu2 equals 30, and mu3 equals 20.
Give me another one. I like that one a lot. Keep going. Give me another one. I'm playing a game with you. Play with me.
mu1 is 30, mu2 is 20, mu3 is 30.
Okay. All right. Megan and yours are the exact same effect size. Did y'all notice that? They said 30, 30, 20. They're the exact same effect size. What if I did 30, 30, 29? Are those the same? That's not the same effect size. That's not the same effect. In fact, that's a smaller effect size. What if I did this? 30, 20, 10. Who's the bigger effect size? Is the bigger effect size 30, 25, 20, or 30, 20, 10? Who's the bigger effect? Who's going to have more power?
30, 20.
Why? You're right. I heard it. More variance. It's the variance among these that is defining the effect. So when you said 30, 30, 30, 30, 20, and you said 30, 20, 30, they're the same numbers. They're going to have the same variance. 30, 30, 29 has very little variance to it. It's a very small effect size. Please don't ask me to calculate that. You will not be happy with me, okay? Note that the combinations in the alternative is just one of an infinite number of combinations, but they're all defining effect sizes, okay? And it's my job to help you mold that effect size toward a design, okay? And I played the game, so we did 30, 25, 25, 30, 30, 25. So we could have all these different possibilities. And here's the take-home message. Stop. It looks very different than the slide I did in the first lecture. I'm going to shut up now, and you're going to interpret it for me. Because though it's not that ugly, though it's not bell-shaped, and though I did not stack them one on top of the other, I will tell you this red one represents the distribution defined by the null. This red one is the distribution defined under your effect size for the alternative. ANOVA is one-tailed test. It's always a one-tailed test, so it only can study one tail. You have to study the upper tail. It is an upper tail test because everything is squared. All calculations, you square this, you square that, you square this. Because you're squaring everything, everything is thrown to the extreme upper tail. So here is your rejection region starting right there. So tell me, what is this little bitty area under the red? That equates to the null hypothesis and the rejection region.
Type 1 error.
Louder!
Type 1 error.
Type 1 error. So this guy here is the type 1 error. What is the power? Oh, wait a minute. What is this underneath the green? Oh, I can't believe I did that after all these years. Power. Right? Now, imagine with me. I like imagination. If I keep increasing the effect size, in fact, I think I'll do this in the next few slides. If I increase my effect size, I'm literally taking my hand and shoving that green line over the distribution. So by altering your, over the line, by altering the effect size or by changing the effect size, I start moving and pushing the green piece over the rejection region. Yes?
Okay, so we've said the area.
You're welcome to sit up here with me.
So this is your type 1 error. This is your power. What is that and that?
All right, that's very good. This is a mistake. This is called beta. This is the type 2 error right here.
Okay.
It is the probability that you do not reject the null when in fact you should have. And over here, this piece is not a mistake. It is under the null hypothesis is true, and it is the region which you would have not rejected. Okay? So this is a mistake area. This little piece here is a mistake area, but the rest for the red is not. This piece is a mistake area, and that is not. Okay? All right? So let's just walk through it. Assume that there's a common standard deviation of 15. We assume alpha. Finally, assume that the researchers believe that at most we can budget 30 per group. They always come back to 30. It's always the number they bring to me. I don't know why. But this is the way it will work out. And that's the scenario I've programmed here. So we'll back up to the graph in a minute, and this is the way I would do it. In a one-way ANOVA study, sample sizes of 30 per group for 3 groups. So total sample size of 90 provides 61.6% power to detect. Differences among hypotheses, notice how I phrased this. The differences among hypothesized means. I just told the review panel, here's the piece you need to replicate it. I give it to you. 30, 25, and 20 using an F-test and an alpha. Okay? The size of the variation of the means is represented by their standard deviation, which is 4.08. In other words, I'm saying, I created the effect size with these means. It maps to this value. Here's everything you need. But if we back up to the graph, how much of the probability is under the green piece beyond that line? What's the number? 61.616. But it is 61.6% of that curve is over that line. That's all we're doing. We are setting up scenarios that shift things. Okay? And again, I play the game here. This is what I would do. I would do a power table and say, here's one scenario, here's another scenario, Here's another scenario. Okay. I think there's a typo in my slide. But these are the different scenarios, and as you see, as the variability goes down, what happens to power? Always goes up. Here we have effect sizes. You see that this here is a smaller effect size than that effect size. These two appear to be mapping to the, yeah, that is true. These two should line up. Be careful that the different effect, because they're different, keep in mind, different combinations can map to the same effect. Okay? And then again, you can do it as you always have. You can say, I want to adjust. Notice, let's back up. I'm sorry. We're not going to go in the study section with the number 61.6. Okay? If you want to try to get by 30, that's too low. It falls to me to come back and tell you if you're going to get to 80% power, you actually need to go up to 45 per group to be able to have an 80% chance of detecting and finding these differences if they actually exist under this set of assumptions. That's all power is. What is power again? It is a swag. What is a swag? Don't say. Just keep in mind, it's an estimate. Okay, what about more complex?
Can I ask a question?
You can always ask a question.
Okay, so it says that last sentence says the common standard deviation within a group is assumed to be 15.
Yes.
So for each of our,
Treatment norms.
yes, we're assuming that the standard deviation
Is the same.
It's never going to be that, though.
Well, now be careful now.
It could be that, but it's highly unlikely that it would be the same.
All right. Excellent point. Counterpoint. Huh? Speak up, Megan.
You have to decide if they're close enough to be able to use NOVA, you're not using non-parametric.
The other reason to keep the statistician around, the answer to the question is, I can interpret the comment two ways. In fact, I can make the comment always true and I can make the comment always false. Honestly. If we're looking at the sample standard deviation of every group, if I calculate the sample standard deviation, there's no way mathematically it'll be the same. Never. But those are all just estimates. And they can vary from each other even if every group has the exact same standard deviation, because statistics always estimate parameters. Statistics will always vary from sample to sample to sample. So it could be, as Megan said, we need to make a decision. When are they so far apart, I can't make that assumption anymore. It's a bad assumption. It's key to understand for a NOVA, a key assumption is they all have the same variables. It is there. It's part of the method. If it's not true, we have to fall to backup methods. I would go to Welch's design before I go to non-parametrics. Okay? What are aerobic standards opposed to treatments? Treatment 2 is a randomization between two drugs. I mean, we can go into some very, very complex designs that all fall underneath a NOVA. So this is all of a sudden this is what I was trying to get to a little bit earlier. I have treatment 1, A and B, treatment 2, A and B, treatment 1. I have 3 levels. Technically, I just created 6 groups. Guess how many means you've got to guess in the alternative in the binary effect size? 6. Okay, so the more complex the design, the message is the more assumptions you must make to get the power. Okay, that's a key concept to you. This is why I'm always trying to tell you, if people don't like it, please keep it simple. please, not for your sake, for my sake, just keep it simple. We can answer simply because the more complex it gets, the more complex the power becomes, and the larger your sample size is going to be. Proportions, we're going to change it again, but it's the exact same idea. Again, what am I going to do? You're going to set up a null, you're going to set up an alternative. If I tell you you're going to compare 3 proportions or 3 groups, how many proportions do you have to come up with? You got to come up with 3 hypothesized values for proportions. And from there, I will get effect size. If you're doing, listen carefully, if you're doing a chi-square table, a 2 by 3, right, or a 2 by 2, how many proportions do you have to tell me? 4. So every time you see a chi-square, or you see a grid, or a cross tabulation that reports a chi-square, you have to understand there was a test of literally, if it's a 2 by 3, there was a test of 6 proportions. All right. So like my teaching example here, you want to be able to say, I've got now 3 migraine drugs. I want to know, does one of them knock out migraines, 40% of all migraines within 24 hours? The other one I'm going to assume is going to knock out 30%. The other one I'm going to assume knocks out 20%. Can I design that study? Understand, here's the same game again. Here's the null. Here's the alternative. You've got to define what's going on under the alternative. Sample size, I need 306 people. I need 102 per arm, thank you. Okay? But if you give me these, it's always the same game. In the back of my mind, there is always going to be a picture in my mind of that when I'm doing the power calculation. Where goes the null? Where goes the alternative? How do I move the alternative distribution above the rejection region? I've got multiple skills that can do it. I can change the sample size, I can change the variance, and I can change the effect size. Yes, ma'am?
How do you decide where your bar is or where your line is?
You don't. I do.
You do. Okay.
Yep, I'm going the wrong way. There it is. There it is.
Okay.
It's right there. The bar is always decided where you put alpha. So let me ask you something. If you decided to say, oh, David, this is so novel. I want to use alpha equal to 0.10, which I've been known to do. I did that when I designed the North in 99. The pilot trials all had alphas at 0.10. Serious. Well, all that does is move this guy back a little bit. But you see, by moving that guy back, what happens to power? More of the green falls above. That's why if you increase alpha, you also increase power. Okay. So let's get ahead so I can get y'all back on schedule because I was generous last week and let y'all go 10 minutes early. Different scenarios, again, all of these help me define an effect size. Once I get an effect size, I can come in and I can start. This is a bigger effect size than this, if you notice. 0.20, 0.25, 0.30, because if for a fixed sample size, this has more power. Therefore, this is the larger effect. That is the smaller effect. And then you see as we increase sample size, moving across columns, what happens with sample size? Always. If you give me more individuals, I have. Okay. These are the basic principles of power calculations. Now, understand something. This scenario, if I was playing this game and going to study section, I would be talking to the investigators saying, you need to, before we even get going, the bare minimum we could talk about the study section would be really interesting in this realm. These other scenarios, maybe they'll let me get by with 75%, but they wouldn't be happy. So again, the idea of meet early with the statistician to start this discussion, it's a good approach. And again, you've seen this. It's not the most important piece, okay? The calculation itself is not the important piece. reviewed 40 grants. I know they were right. I know they did the calculation right. I still had to triage the study because they didn't put the information in that would allow me to confirm. As we design grants together or projects together, aims must match. The aims are all that matter to me. That's all that matters to me. Once you give me the aims, we'll work toward design, we'll work toward outcomes, we'll work toward analysis and power. But understand, is analysis and power are the end, not the beginning. And the other thing that's a killer at study section or killers on papers between the analyses and the approach does not match the aims. You can't have that happen. There's no bait and switch. So the bottom line is, you can drive, I would say this, and I'm not trying to be cocky or arrogant. 2 sample t-tests, 2 sample proportions. I'm perfectly fine with anybody trying to do those calculations. Bring them to me and say, can you confirm we have everything right? No problem. You get into ANOVA, you get into regression, you get into something like that, get the methodologies, and work from there for the time. All right? And that is that. And I gave you 8 minutes. Now you can check your email.
Oh, yeah.
So you're walking to the next appointment?
I'm first going to sit here for just a minute. I have not even logged in yet to see what's going on. And then I'll be walking to a meeting and then going from there.
Yeah, I mean, I would have.